So it's my great pleasure to introduce Professor Bill Langdon. Bill did his undergraduate from physics at the University of Cambridge, and then a PhD in computer science. He spent 13 years in industry, and he's a world leader and expert on genetic improvement and genetic programming, having written 3 books on the topic.
And so there's a copy of one of the books.
Copy, which is this the only copy you brought with you?
Yeah, that one has to go home.
Oh, but who's home? Anyway, my great pleasure, Professor Langdon.
So thank you very much. So my plan is essentially to talk about long-term evolution experiment with genetic programming. And then what happens if we run the GP for a huge length of time, 100,000 generations. This is made possible by exploiting some work on vector instructions, which is actually being optimized using genetic improvement. And that work's going to be presented at the GI workshop here at ICSE. What we see is during the course of evolution, we continually find new improvements, but the rate at which those improvements occur falls as the programs get bigger. The second part might be the most interesting from a software engineering point of view, is we're going to look at what happens inside the programs. Essentially what happens to the information, and we're going to quantify information in terms of entropy. And so there'll be a little reminder about what entropy means in terms of software engineering. So the background to this is some work by Rich Lenski. So in his first postdoc in 1988, 38 years ago, he started an experiment which is still running. The guy's retired, but the experiment's still running. And when he started, he was told that if you put bacteria into a standard flask, very standard conditions, we know exactly what's going to happen. It's going to evolve to meet the conditions in that flask, and then evolution will stop. So why do the experiment? And he ignored the people who said, we know the result, and he went on and did the experiment. And as I said, that experiment is still running. And what happens is the bacteria continue to evolve. So even after 38 years, the bacteria are still evolving. And it's a picture of him fishing out samples from a deep freeze. Samples are frozen in liquid nitrogen. So inspired by that, we thought, well, okay, let's run GP for a really long time. And this work was presented here about a year ago. And that was work using traditional GP, using tree-based GP, running out of eventually to 1 million generations. Here we're going to look at a different type of GP. It's linear GP, so we just have a linear list of instructions, arithmetic operations. And here we're going to limit the size of the programs to 4 million nodes, and we're going to run the experiment. And the nice thing about computer science is you don't have to spend your entire career on one experiment. So we could run the GP, and even the longest of the runs completed in 12 days. The system we're going to use is based on Peter Nordin's GP engine. We start with population of 500 fairly short programs, and we're going to evaluate them on a chaotic time series. The goal is to predict the next time step. So it's chaotic, can't really be predicted, but we wanted something difficult to keep the GP occupied. I'll come back to most of this during the talk, but essentially it's a standard GP. We're trying to predict this time series. And so it's IEEE benchmark. We're going to take the discrete form of this, so everything is evaluated in bite-sized integers, so 8-bit integers. And we've got 1,201 time samples. You're going to see lots of stuff about entropy later on. The right-hand screen there is just showing the histogram of time samples. So you can see values around 32 seldom appear, whereas there's a lot of samples around about 144. So you'll see that histogram later on. And the way the GP is set up, it's like many time series predictions. This is used a lot in financial forecasting. You take time samples from previous history and use those as a way of predicting what happens next. Most useful symbol is always what happened one time step ago. So what we're actually going to do is we load previous history into our 8 registers. So register A gets something from the time 128 samples ago, register B 64 time steps ago, all the way down to H, which is 1 time step ago. And the goal is predict what happens now. And as I've said,
why those particular intervals? Is there?
Their powers are 2.
No, yeah. Apart from that, no other.
No, I mean you want some close to where you are now. So what we would anticipate is H, G, and F to be the most useful, and probably the others be rather less useful. And it's certainly H is by far the one most preferred by the evolution. In terms of creating the new populations, what we do is we select 4 individuals from the current population. They're 4 different individuals. What I've shown there is at the top, the better 2 are selected parents. The worst 2 are wiped out and replaced by the children. So we create from our 2 parents 2 children. The red at the top represents a linear program. So we start copying from the red parent into its first child, and then we do a crossover, and at some randomly chosen point, we start copying from the blue parent instead. And that's how we create the 2 children. And in addition, on top of that, we throw in up to 4 just random mutations. So these are just single changes, whereas the stuff where we're copying, we may be copying large amounts of program. So shout at me if this is not making sense. So we run the GP 10 times and we get those 10 different runs. From my point of view, what's interesting is the GP is continuing to evolve, it's continuing to find better solutions. Initially very rapidly, but as time progresses, the rate of improvement doesn't go to 0, but it gets less. The other thing that was entirely predicted is the programs get much bigger. So we imposed a limit of 4 million nodes, 4 million instructions. And you can see all the runs, the programs get bigger. Only in one of them do they get continuously bigger. So run 6 is a smooth curve going up to the maximum. The others do something weird in between. And there are a few runs where we don't actually reach the maximum. But they're all showing really excessive growth in the program size. In terms of the experiment, what I plotted here is the rate of improvement. So rate of improvement is on the y-axis, and the straight line is RMS best fit curve. So we're plotting a linear regression. You can see the data's all over the place, but nonetheless, the linear regression goes through the origin, indicating that the rate of improvement is falling inversely with the size of the program. Okay, so the last bit I want to say is we've run this And then what we want to do is try and understand what's going on inside our programs. And this is using information theory, and in particular using entropy to quantify how much information there is within the program. By information within the program, what I mean is the pattern of data within the 8 registers. So it's a very small system. There's only 8-bit registers. We define entropy in terms of this summation over probabilities. So entropy is always defined over distributions. The distribution we care about is the distribution over the test cases. So we've got 1201 test cases. That's going to give us a distribution of memory values within the program.
So you're only doing the distribution on the visible register, which is like the 8 of them.
Yeah.
And all the value you've seen after evolving it for enough time.
Yeah. So we'll start at the first instruction where the contents of memory is given entirely by the inputs. Then the second instruction, well, we overwrite some register. And then we progress on and look at how entropy changes as the program runs. And again, it's all over distributions, it's all over the test cases. Okay. One view of entropy is essentially a way of measuring how surprising the distribution is. So if we have a very rare event, then it has a very low probability, which means minus log of that probability would be bigger. And essentially, the summation over pi is effectively forming a weighted average. So one way of looking at entropy is the average surprise for distribution. Again, a very simple system. So just to give you that flavor, supposing we have something which has 2 events, P and Q, which either P or Q happens. So we toss a coin, either we get heads or we get tails. What this curve is showing is the distribution of entropy according to the probabilities. So maximum entropy of 1 bit when P and Q are equally likely. So we don't know in advance what's going to happen. Whereas if one of our probabilities is much more likely, so if we have P of 1, then the entropy is 0. Essentially, it's a constant here. The distribution is always flat. There's only one thing that happens, and that gives us an entropy of 0. And the curve is symmetric, so if we had tails instead of heads, again, we'd have an entropy of 0. Getting nods in the room, so I'm going to press on. 2 distributions which quite easy to calculate the entropy of. The uniform distribution on the left-hand side, the entropy is log 2 of n if we express our entropy in terms of bits. Another nice result is we can actually define entropy of continuous distributions, in this case, the Gaussian distribution, and we get the result that the entropy is 2.04 plus log 2 of the standard deviation. So the critical thing is always log 2 of the width of the thing we're dealing with. And there's a constant at the front, which changes. But essentially, if you calculate entropy and you don't come close to either of those, maybe double check you've done the sums right, because you've almost always entropy is somewhere in that ballpark. So what we're going to do is we're going to take some programs and we're going to actually run them, and then we're going to look within the program as it executes. And the distribution we care about is the distribution over the test cases. So when we start, we always have the entropy is the same as the entropy of the test cases. We have deterministic programs, so there's no way for the program to get more information. it can only lose information. So when we terminate the program sometime later, the entropy within it can only be the same or smaller. And similarly, the entropy of the output can only be the same or smaller than the entropy in the program when it finishes. So we have this inequality. If that inequality is not holding, then something really bad has happened. And that might be a useful signal. That might be something we can use as an intrinsic test oracle. So if we're fuzzing, when we're fuzzing, we never know what the correct answer is. We have essentially two test oracles. Did the program crash, or did it fail to terminate? This is potentially a third one. Also, we might have an external device which monitors the memory, and again, maybe an external device can calculate entropy within the system. And if something is going wrong, maybe it can send you an email, maybe it just reboots the thing. But that's potentially an external monitor which could be independent, which doesn't really care what the program is trying to do. So we don't need to specify in detail what the program is doing at this point.
Just have this about, can it be a test oracle in quantum as well? Because you take a distribution and instead of like mutating the code, you're just mutating the environment, because the shots each time do slightly something different, and ask the same question as a test oracle.
So the question was from Corinne, can we use this in a quantum environment?
Yeah.
And the answer is yeah, sure. It's even cleaner in a quantum environment because every operation is reversible.
Yeah.
So we should never lose entropy. We should never gain entropy.
Yeah, that's what.
So potentially you can replace these inequalities with equals.
So if you do like a state vector, this should be equal always. You just take the entropy before and the entropy after.
Yeah, that should be feasible to do that.
How could a program increase its entropy? I mean,
Something has gone wrong.
very wrong, but what?
Well, for instance, maybe something has come in and corrupted your memory.
Okay.
Maybe the program is to do what you thought it was doing. Maybe it's actually reading inputs as
There must be an external source of information which you're not aware of. That's
or just noise.
okay.
Something that is untoward is happening. And this is strictly true for batch programs, but you could adapt this for iterative programs as well.
I mean, did you actually observe this happening?
No, this is scope for the software engineers in the room.
Not me.
But that's a very
It's interesting.
it's a very useful one.
I mean, I guess it's quite rare, but it's an easy check to make.
Yeah. So you had to
You don't
monitor.
think it's rare?
I don't think it's rare. I think we just don't check it.
Maybe.
That's why I suspect. That's why I ask you about the quantum. It's like
Yeah.
I took a picture. That's a good one.
Oh, you can have copies of the slides. Anybody can have copies of the slides.
No, but this is I will look at the book, but this is really
So that's more or less what I said. So what we're going to consider now is these are results on the full run. What I'm going to consider now is just running for the first 500 generations. So the programs have already adapted. Some of them have grown quite long, but at this stage, essentially the interesting things are already happening, and we can then stop and look at the entropy in programs at generation 500. So this is one particular run. The other runs behave pretty similarly. The purple lines are programs that have been created in generation 500, which are worse than their parents. So their parents were always above average. What the 6 purple lines you can see at the bottom is showing are these programs run and terminate normally, but their internal entropy is way below the target. In particular, there are several where the entropy goes to zero. So that means at this point, the program is going to create a constant.
But if you did have noise in the system, eventually it should uptick again, shouldn't it?
Well, these are noise-free systems. So it entirely depends on your model of noise. But the point is, when we get to say, we've run 100 or maybe 150 instructions, the entropy is now fixed. It cannot go below zero. We know in advance it's a useless program. We can now stop execution. The interesting, again, from a GP point of view, is all the programs start off with the entropy of the inputs, so 10.2-ish in this example. And the green guys go down to something that's very close to the entropy of the target. In other words, there's serious hope that these actually emulate the target very well. The things that go below the target are probably not going to be helpful. Potentially we can save ourselves a lot of resources by cutting short their evaluation early. So, oops. That's more or less saying what I've just told you. I'm going to take one example. So of our several hundred examples on that plot, I'm going to take the first one that actually gets the value and concentrate on what the entropy happens as it executes. So you notice the x-axis is a log scale. So what we see is from about instruction 45 onwards, the entropy is rock solid. It does not change at all. I'm going to show you the result of the G equals F times 24, just to show you where that big fall in entropy comes from. And then I want to concentrate on the long tail, what is going on there. So the purple at the bottom is the distribution of memory values across our test cases before we execute G is F times 24. So we have a fairly wide distribution there. I think there are more than half of the test cases have different unique memory values. Then we execute F times 24 and overwrite generation G. Register G. And what that does is all the memory patterns which only differed in the contents of register G, now they're all the same. So I've highlighted two. One starts with A is 1, B is 60, and so on, and G is 110. There's one instance of that in the memory. And similarly, on test case 23, register G has value 92, but it's otherwise the same. Because they're otherwise the same, the instruction must generate the same output. And what we're going to do is we're going to overwrite register G with the same value. So suddenly, instead of there being unique memory patterns, we're in the position in the green where those two memory patterns become the same. And this happens in a large number of different cases. And suddenly we go from having 687 unique patterns, we're down to just 129. And the next instruction comes along and knocks that down to 128. That 128 is solid for the next 10,000 instructions. I'm getting nods from the audience, so I'm assuming this is making some sense. Yeah, and we can calculate the entropy of those distributions.
Unless it's randomly read, right?
I'm sorry, can we?
I said that unless there is random. Oh, but even random. I guess if like you just chop it in the middle and do random forward the register. I'm not sure how the entropy would behave there.
Well, so remember, these are all deterministic programs.
Okay, yeah, okay. So that's in
So what I've done is the colored histogram is a distribution of memory values at instruction 200. 200 was chosen at random. And we execute an instruction. We get back at instruction 201 exactly the same distribution. And I thought, wow, evolution has been dead clever. This is fantastic. And I got a bit suspicious. Pretty much any random pattern has this property. I have generated tens of thousands of random patterns, and they all, within this context, they all have this property that the next instruction doesn't change them. So I wanted to show you what happens with instruction 200 and then leave you to extrapolate on all the other 10,000. So what we're going to look at is the instruction A is G divided by 42. So from a straightforward point of view, you think, well, we take values which are scattered between 0 and 250, and we divide them by 42. We're going to get values between 0 and 6. Therefore, the entropy must go down, which is true, but it's only true of the output register. The contents of the entire memory does not change. The entropy contents doesn't change. In fact, the distribution doesn't change. So the horizontal crosses are the distribution between register A and register G before this instruction. So you can see they're already highly correlated. What the arrow is doing is showing just one test case. I think it's the first one. We start off with register G having the value 66. We're going to divide by 42. So whereas register A had the value 156 beforehand, it now has the value 1. And what the diagonal crosses are showing is the contents of register A after this instruction. So it's all behaving as expected, but this transformation doesn't change the distribution. Distribution doesn't change, the entropy doesn't change.
it's just like a mapping, right?
Sorry, Chris.
It's a mapping function.
Yeah. And although by itself this is A divided G over 42 is irreversible. In the context, it maps one set of memory to the next set of memory, which has the same distribution. And that distribution, as I said, doesn't change over time as we continue executing the program. And that's distribution of A before and after. So you can see it's highly structured. We do lose entropy locally, but not across the whole of our 8 registers. So the last bit is me going back to the GP. So I'm going to look at what happens in our program, which is composed of code from the 2 parents and also mutations. So essentially what happens on the right-hand side, so the purple code has come from the first parent. In the middle, the green code has come from the second parent, and then we go back to executing the first parent code again. The numbers, so XO52 means this is the start of our crossover point, and the 52 means the 52 instructions after the boundary, the contents of memory are different, but then goes back to 0. So this program calculates exactly the same answer to the parent not only is the answer the same, but the contents of its memory the same, despite the fact that we swapped to executing code from a different program and then swap back again. And in this example, we've also got 4 mutations. So what I'm going to concentrate on the purple line. So the purple line is what happens when we cross from the first parent into the second parent. And the y-axis is the number of registers that are different, even by 1 bit, across the test cases. So 7206 means on average, we have 6 registers which are totally different on all, sorry, not totally different, they are different on all of the test cases. So you can see the crossover operation where we swap to a random part of another program is highly disruptive. There's only 2 of the registers, on average, only 2 of the registers are unaffected. But you can see that as programs execute, the trace of difference wobbles up and down and eventually reaches, after 52 instructions, reaches 0. Meaning from instruction 53 onwards, it's executing exactly the same memory patterns as were in parent. The easy one to see is the little blue cross down in the corner, which represents mutation at instruction 9219. And what that is from memory was to change the value that's written into register A. The instructions mutated. In almost all of the test cases, it calculates a different value. Not all of them, but most of them. So register A now has a different value, but only register A. The next instruction in this example overwrites register A, and it overwrites it with something that's calculated using the other values in machine. So those have not been disrupted. We calculate the new answer is exactly the same as the previous one. So any disruption that was loaded into register A is immediately gone. If you look at the big green squiggly line mutation 4271, you see it's not guaranteed that the next instruction is going to wipe out the instruction. In the paper, it goes through this in tedious detail, but the point is the disruption, at least in this example here, we start off with 1 register that's being disrupted, and nothing much happens until we get to about 20 instructions later, when that disruption is copied to another register. And then it comes back down again. And then round back instruction 23, it goes up, and then instruction 24 copies it again. So by instruction 24-ish, we've transferred our mutations impact to 3 registers. And you can see it waggles about a bit, and eventually it reaches a point where 6 registers have been disrupted. But from there on, it comes down again. I should stress this is a fit program. So despite these limitations, it's still actually performing. You can imagine other mutations where it broke the code. But one of the things that's always been claimed about GP is the code is fragile. And I just want to show it's not necessarily true.
How many did break?
Maybe about 40%.
And the rest exhibit patterns similar to this.
The ones I've looked at. And yeah, it's kind of very tedious and long-winded to actually do this, but you get something similar.
But can you actually use this signal to improve your mutations?
Oh, potentially. I mean, I haven't tried. If about half my programs are still working after mutation, that's good enough. I don't need it to be 99%.
Is there any correlation between size of program? Oh no, your program's always the same size. It's just
No. The programs grow in length.
Okay, so is there a correlation between entropy loss and the size of the program, like when it occurs? So if entropy loss occurs later, the program is bigger, smaller, no difference.
Let me show you that later on.
Okay,
I haven't got an exact answer.
you've got about 10 minutes left.
Oh, okay. So fortunately, David has now raised the question of what happens, why is our innovation falling with program size? So we run longer, we get bigger programs, the rate of innovation falls. This is all for generation 500, but it's across 10 different runs. What I've done is sort entropy. So you don't start off with a nice curve like this, but it's been deliberately ranked so that you get the high entropy at one end and the low entropy at the other end. And what I've done is sort the children into three classes. Those that have the same performance as their parent, those that are better, and those that are worse. The exciting thing from my point of view is there are approximately 1,000 children where the crossover landed in a high entropy region. So those are regions near the beginning of programming, near where the inputs are. If the crossover lands in entropy near value near 10, then it's very likely that crossover is going to disrupt them. So they may be better or they may be worse, but they're not the same. If the entropy is down near 6, in other words, in the long tail, then it's no clear signal. Sometimes it's better, sometimes it's worse, and there are a sizable fraction where it's the same. But what appears to be happening is in the high entropy region, the code is much more sensitive. So if we target mutations at that point, we might actually get more broken programs, but we might also get more better programs. Okay, so what I want to do is just conclude here. What we started off doing was running long-term evolution experiments. I said we're out to 100,000 generations. I should have pointed out that as a species, we are about 9,000 generations old, approximately. Best estimate seems to be 9,300. So in other words, 100,000 generations is a really long time. We can run these experiments in a single computer in maybe a fortnight, certainly weeks rather than 38 years. What we see in the linear GP is the rate of innovation falls as the programs get bigger, which is an argument for stopping the programs getting bigger. But one thing that's interesting is the linear GP, the sensitive region seems to be at the beginning of the program, whereas in the tree GP system, it appears to be near the outputs. What I've argued is, in terms of entropy loss, this is a property of deterministic programs. So any batch program that doesn't have a source of noise or isn't sneaking information in from the outside should have these properties. If we want to build a program that predicts, then we would expect the entropy to fall to near the target. Nice thing about that is we don't need to know in advance how to build that program. We probably know what the target is, otherwise we really are guessing.
But how do you calculate that target? Because that was my next question. Where's the target come from?
Target's coming from what did you want the program to do? If I wanted a program that sums the numbers 0 to infinity, not so good, but 0 to 256, well, we can precisely define the mathematics of the entropy before we've written the program.
So I'm going to guess that your test suite, so the initial entropy is the test suite's entropy.
The initial entropy, but
Yeah.
I'm talking here about the target.
No, fair enough. But so I noticed that your entropy was about 10 bits, something like that. So that's probably close to the max, my guess. What happens if your test suite is deficient? What if you've got a lower entropy than the target? Or you've got less play space, less headroom?
If your entropy on input is less than the target, you're
knackered.
There's no way that you can get a good solution. This gives you a bound on how bad the solution might be.
Is there any way that we could, like, say, so if your entropy of the test suite was below the target entropy, we should be able to calculate maybe how many more tests or what we need in the tests in order to bring the entropy up?
Actually, yes. Yeah, that's a good point. Yeah, and the point being, you can do this without having written the program. More the point, you can do this if you get a machine to write the program for you.
It's a kind of like a stopping condition.
Yeah. Yeah, so you wouldn't even bother starting if your entropy on the test suite was low, because then, well, this is insufficient. Let me do this first, and then save an awful lot of wasted effort, potentially.
Yeah, potentially. Yeah. And as I say, you can do this before anybody's attempted to implement anything, or before a machine has been set loose on it. I talked a little bit about using entropy as an implicit test oracle. I suspect that would be interesting for the people who are doing fuzz testing. It requires more instrumentation. You need to know what's happening inside. Essentially, that's all available.
If you look at coverage, or it's too high to add granularity, like you find that.
The coverage is part of it, but you need to know what's actually inside the memory. So it's not
have like
just
a memory snapshot or so.
Yeah, and you don't need to run this continuously. You could take a series of snapshots.
Yeah, you don't do like every
And one last thing is, I didn't stress this, but if we remember back to the histogram, by instruction 45, we had locked into that histogram, which says, in fact, there's only 128 memory patterns in the machine. So we actually only need to run 128 test cases. So we would potentially divide our testing effort by 10. Requires a fair amount of analysis to decide which are the 128 matter. But again, it's potentially a way of short-circuiting the evaluation. The last bit is me pontificating, really. So Royal Society, leading learning society in the world, founded in Charles II's era. Their motto, which is down at the bottom, only written in Latin, so I assume everybody is going to be able to read the Latin.
It's too small.
Nulli in verba, which translates as take nobody's word for it. Rich Lenski was told very firmly, we know what happens, don't do the experiment. They were totally wrong. From the point of view of genetic improvement, genetic programming, automatic program repair, 20 years ago, the idea that a program could fix bugs, really ludicrous, totally impossible, until somebody actually did it. they hadn't been told it was certainly impossible before they started. That was a PhD student. And we now have a situation where automatic programming repair is a thing. The only argument is whose technique is the best one for doing it. So the idea it's impossible has been totally wiped out. So what I would suggest is we've got incredibly powerful AI systems. Get them to do something which nobody else has ever considered. That's the way to get famous. Okay, I better stop.
So is that the Alice in Wonderland? That's just
Oh,
why she there?
so for those who are familiar with, this is Alice Through the Looking Glass. Alice is talking to the White Queen. So the White Queen has just said something ludicrous. And Alice retorts, oh, but that's totally impossible. And the White Queen's response is, oh, but you must practice thinking of the impossible. When I was your age, I could think of 6 impossible things before breakfast.
Right, well, let's thank our speaker. So very quickly, are there any questions in the room? We probably asked them any questions online. Oh, lots.
Thank you.
It's very useful.